All right, so here we are again, and so we'll just pick it up where we left off yesterday. We're about to look at a proof, first proof of the semester. It's not exactly what you're used to seeing. Finance proofs can be very different than what you see in math. The way they're approached, the objective, what we're trying to accomplish, but I mean, the logic is, of course, exactly the same, but the approach may be a little different. Here, what we're just basically trying to demonstrate is why the future value of the sum is equal to PE to the Rn power when we have what we call continuous compounding. In other words, n is equal to infinity. Okay, or actually, sorry, not n, m, as m is in Mary. M is the compounding frequency as m approaches infinity. Limit as n m goes to infinity. Equals, I should say, not converges to, equals PE to the Rn. So we're going to see a very quick demonstration of why this is the case, based, of course, on the definition of E as 1 plus, or actually, sorry, E is the limit as x goes to infinity, as we saw yesterday, 1 plus 1 over x to the x power. All right, so we're going to use the same logic to demonstrate why the future value of the sum is equal to PE to the Rn power. So by the way, just as a quick reminder from yesterday, R is the rate of interest. Hold on 1 second. There we go. N is the time. Okay, and M is the compounding frequency. Okay, so for example, if the interest rate is 8% per year and N is 5 years, M is the compounding frequency. And so if the compounding frequency, for example, is quarterly, that would mean instead of thinking in terms of 8% for 5 years, it would be 2% for 20 quarters. Okay, so that's why the formula is set up this way. But as M keeps increasing, the interest rate shrinks, but the number of time periods increases. And in the limit, it actually converges to PE to the Rn power. So here's why. Well, first of all, here's what we're going to do. We're going to do a little bit of an algebra trick. We'll start here. Of course, what proof is not based on algebraic tricks? I mean, really, when you come right down to it. So basically what we've changed here is the exponents. Okay, so now if you notice, just in general, the power rule for exponents tells us that if we have a to the m power, which is all raised to the n power, the result is a to the m times n power. So here, what they've done is written this in such a way that if you notice m times r, over r rather, times rn, is still mn. Okay. What's different is the way we've written it. And so the exponent hasn't changed. But here's what this lets us do. We're going to take and replace the m over r with the letter k. Okay, this will be a new variable. K will be used to represent m over r. So that means this is 1 over k, and this is k. Okay, now we're only doing this because it makes it easier to see the connection with the definition of E. So if you look in the next slide, you'll see that now this is what we have. And of course, if we take the limit as k goes to infinity of 1 plus 1 over k to the k power, this just gives us E. So by doing it this way, we take the limit, and this reduces to E The exponent doesn't change. So we end up with PE to the RN. Okay. And of course, that implies algebraically that P, the present value, equals FE to E times E to the minus RN power. So future value is PE to the RN power. The present value, or P, is PE to the minus of, sorry, FV E to the minus RN, or if you prefer, FV over E to the RN power. So this is very important because, as I said before, the material that we're using for this class is based on John Hull's book. And even though in practice you don't normally use continuous compounding, it has some very convenient mathematical properties compared to discrete compounding. So we often see derivatives models being expressed in terms of continuous compounding. And Hull's book, Hull goes a little bit further than that. He uses it for everything. It's like he's decided that discrete compounding isn't the best way to model financial variables. And so he uses it even when a lot of other authors don't. So we want to become very comfortable using continuous compounding. Anyway, with all that being said, we're ready for annuities. Now, I mentioned this yesterday. An annuity is an annual stream of equally sized payments. Okay, so in other words, what makes it an annuity is that the payments are all identical to each other and they occur once a year. So I mentioned the example yesterday of the lottery winner. If you win an unusually large prize, it's very rare that you actually are given the entire amount right up front. Often what ends up happening is that it's split up into payments. For example, a $10 million lottery prize might be paid out as $1 million a year for 10 years, and that would make it an annuity. Now, these can be structured in one of two ways. The first type is called the ordinary annuity, as you can see, and the second is the annuity due. And so what really separates them is when do the payments start? Okay, so basically what it works out to is that the ordinary annuity, which is the one you see the most often, by the way, the payments start next year, and with the annuity due, payments start right away. And of course, the reason why we make a distinction between these two is that, of course, it makes a great deal of difference to the present and future value of the annuity, the timing of the cash flows. So we need to make sure we always know which one we're talking about. Now, these formulas that we're seeing here are designed for ordinary annuities. If we have an annuity due, we have to make an adjustment. Okay, so when you see a formula like these, you can usually assume that it means an ordinary annuity unless it tells you otherwise. That's the standard. So now you might think that this would be a horribly complicated formula, given that the number of cash flows can be anything. It could be 10, 20, 50, 100. But yet, it all consolidates very nicely into a single, relatively simple formula. Now, if you notice the notation here has changed a little. FV has been replaced with FVA. The A means annuity. And then the P is gone. P is principal. C is being used to represent instead the annual or repeated cash flow. But R hasn't changed. R is the rate of interest. And N is the number of years or number of time periods. So if this is a 10-year annuity, then N is 10. All right. So let's see an example of this. $1,000. By the way, we're going to do these in Excel again because it makes the most sense, although you certainly can feel free to try this on your calculator. So what do we need to know? First, we have a sum of $1,000 is invested at the end of each of the next 4 years. So that's how I know that this is an ordinary annuity. Okay. So the end of this year, the beginning of next year, it means the same thing. It is a year in the future. So we have 4 of these payments. So remember now, instead of using P for principal, we're using C for annual cash flow. So therefore, C is $1,000. R, the rate of interest, is 3%. And that leaves us with N, the number of years, which is 4. And we're trying to figure out the future value. Now, I'm going to copy the formula here so we don't have to keep scrolling back and forth. Oh, actually, I forgot. I just realized I violated the notation. It should say FVA. All right, so let's try this. Now, this is the thing about Excel formulas is that there can be so many parentheses that can get very, very confusing. So what I'd like to do is start with the most, let's say, messy part of the formula and sort of work back out to the rest of it. So I'll start with 1 plus r to the n power. Now you don't have to do this. I just find that this makes it a little easier to avoid mistakes. Then I can subtract 1. Now all of this is my numerator in that form, within the brackets, that is. I'll divide that by r. And then all of this is ultimately multiplied by c. And there we go, 41.83. And we'll round this to dollars and cents. Okay, now, of course, in this case, the principal that we invested in this is 1,000 times 4. Okay, so in other words, the investor is putting this money in the bank every year. So altogether, the total investment is $4,000. Okay, or in other words, C times that, which implies the interest that was earned is the difference between the two, which of course would then be 183.63. Now, it would be very messy for us to sit down and try to figure out how much is simple and how much is compound. We could do it. We're not going to do that right here, though. What's important is to note here that we have some amount that we invest every year. And so this simple formula enables us to calculate the future value very quickly and easily. Without this formula, we would have had to calculate the future value of each individual cash flow separately and then add them up. Okay, so in other words, what's actually happening here is for cash flows of $1,000. First one is being invested for 3 years. Actually, I'm going to have to change this drawing just a little bit, because I need to also show that the second cash flow is invested for 2 years. The third one is invested for 1 year. The last one actually has just been deposited in that same year. So I could, in principle, calculate the future value of this first $1,000 plus the second one, plus the third one, plus the fourth one, and I would get the total would be 4183.63. But we don't need to do that because we have this formula. Now, having said that, and by the way, I guess we could try it right here. So remember how this works. The future value of a sum, we're multiplying the $1,000, which is B1. Now, by the way, I'm going to show you a little trick here in Excel. These dollar signs lock in the reference, so I don't have to keep changing it. This one will never change. No matter where I copy this formula, it'll always refer to B1. I'm going to multiply that by 1 plus the rate of interest, which is B2. Also, this needs dollar signs. Now, here's the interesting part. The exponent is equal to the total number of years minus the year in which I make this payment. Okay, so in other words, right now, this would be 3 years. The next one would be 2, 1, and then 0. Oh, you know what I did? I forgot the dollar signs for B3, sorry. After all that discussion, that's also a constant. So all the constants need these dollar signs in order to make sure that they don't change. And you can see if you forget, that's exactly what happens. There we go. So if I add these up, it'll be the same as what we just had, except possibly for some small rounding differences. So no, it's the same. Okay, so in other words, this formula just did this. In other words, it calculated the future value for each individual cash flow and added them up. That's where this came from. Okay, excellent. Now, what if this had been an annuity due? Okay, well, that means the cash flows, the pattern of cash flows would be a little different. Let's see. I'll draw this down here. So I'll just copy these and I'll draw the graph again, except you'll notice this time, first cash flow is in year 0. Then we have year 1, year 2, and then year 3. Whoops. And then there's no cash flow in year 4. So this first one is being invested for 4 years. This one is 3 years. Here we have 2 years. And here we have 1 year. So each cash flow has been invested for 1 extra year. So if I construct a chart like this one, I'm going to change that exponent. And instead of subtracting A1, I will just have it as that number. In other words, actually, no. Here's what I'm going to do. Sorry. What I'm going to do is subtract 1 more year. Oh, no, sorry. Here's what I should have done. Instead of doing, no, I'm going to do this. 828 is not what I wanted. It's no wonder it's not working. 821 is 4 right there. And all right, well, let's try that again. B3 is 4. So what I'm going to do is, oh, I know what the problem is. No, I guess that's not the problem. Oh no, it's still the wrong reference. It's supposed to be referring to cell E28. That's what the problem is right there. All right, now we're getting somewhere. Perfect. Okay, so what I was trying to do is make sure that this cash flow is being invested for 4, 3, 2, and 1 year. Okay. So the total is suddenly 4309.14 instead of 4183. And the reason for that is because each one of these has been invested for 1 extra year. It's bringing in an extra 3% worth of interest. And so that raises the entire sum from 4183.63 to 4309.14. Now, none of this was absolutely necessary because here's what I could have done. Future value of an annuity, I'll put in parentheses ordinary, times 1 plus the rate of interest equals the future value for the annuity due. Basically, you're just multiplying all the cash flows by 1 plus R, and you'll get the same result. So let's prove it. Here, this one was 4183.63. If I multiply this by 1 plus the rate of interest, which is here, you'll see that it works. Okay. Beautiful. Except, yeah, no, that's right. 4309.14. So either way, either just recalculating each of these with 1 extra year and adding them up, or multiplying the results from the ordinary annuity by 1 plus R, either way, you'll get the correct value for your annuity due. And this diagram shows you why. Okay. It's that extra year worth of interest for each cash flow that's causing this to happen. Right. Now, you can imagine we're going to have the reverse in with the present value. So we have a separate formula for the present value of an annuity. Again, we'll change the notation. This time it's PVA. And let's see. Why don't we do some examples? All right, so here's the formula. And you can see, once again, C is replacing E because it's an annual cash flow rather than a single cash flow. And then, of course, we know what R and N mean. This time, we'll have 5%. And it's 3 years. And the cash flow that we want is $1,000 a year for the next 3 years. In other words, we want to put X amount in the bank now, which enables us to withdraw $1,000 every year for the next 3 years. Okay. So you can see how this would apply to some important applications. Imagine you're trying to plan for your retirement, and you've decided that in order to retire comfortably, you need to be able to withdraw $100,000 a year from your account when you reach 65. And let's also assume that you're allowing 20 years or more. Who knows what's going to happen in the future, but you make some decision. And so you need to know how much to save now to make that possible. So here we're going to calculate PVA. And this will just let us know how much we have to put away now in order to make sure we reach our target. Now, again, this is an ordinary annuity. So the payments will start next year. However much I put away, actually, I'm sorry, we're putting the money now, but we're drawing the money every year starting next year, not right away. So let's use this formula. So let's reproduce the exponent, the numerator here first. Yeah, the one thing about parentheses is you can help avoid mistakes if you just count how many left parentheses there are and how many right parentheses there are. You've got to obviously match up. Here I've got 3 left parentheses and 3 right. If not, I know something's wrong. Now that's my numerator. The denominator is simply R. Okay, I was trying to move this out of the way and I goofed. Here we go. By the way, also Excel is trying to be helpful. If you notice the colors here, it's trying to make sure that the lefts and the rights match up with each other. It looks like I've got the right number of each. And then what I wanted to do is divide all that by R, but that's only what's in the brackets. Now I need another round of parentheses so that I can then multiply the whole thing by C. And yeah, okay, obviously something went wrong. All right, obviously when I tried to move that equation, it did something I didn't expect it to do. See, that's why I gotta watch that. All right, I'm gonna put it somewhere where I can see it. All right, let's try this. 1 minus 1 plus r raised to the minus n. That's my numerator. Now, they're surrounded by parentheses. Divide by r. Now, all of this is what's inside those brackets. And then finally, we have times c. Now, that's got to do it. That's it. That's it. Okay, great. Now, how do I know that, by the way? Because we're going to withdraw $3,000 from this account, 3 years of $1,000 each. So this PVA has to be less than $3,000. So what this is also telling me is that the interest that I've earned first, the total withdrawn is 1,000 times 3. And so therefore, the total interest that I've earned is the difference between the two. Okay. So now again, this is assuming that this is an ordinary annuity, meaning that the cash withdrawals don't start until next year. If that's not true, then we have to adjust the formula. So what we've done here is we've created an ordinary annuity of $1,000 a year for 3 years with an investment of 27, 23, 25. Had this been an annuity due, meaning that the cash flows start right away, then I would have had to do something a little different. Now, if you recall from just a few minutes ago, oh, now wait a minute. Wonder if this applies to present value. Let's find out. Well, the answer is yes, except it's now PVA. It's the same adjustment. You multiply by 1 plus R. So if this is an ordinary annuity, meaning that cash flows, the cash withdrawals start right away, then the amount that must be invested. Okay, and so we're going to remind ourselves that ordinary is 27, 23, 25. Therefore, PVA annuity due is this number times 1 plus R. And when you look at it, you'll realize that it makes perfect sense because the total withdrawn is still $3,000. And that implies that the total interest is less. And of course it is, because there was less time for the money to accumulate interest. Okay, the money was being withdrawn sooner, therefore there was less interest, and therefore we have to put more money in the bank now in order to reach the same goal. Okay, so as far as the diagrams go here, we deposited 27, 23, 25 here. Now, in this case, we want to keep track of the signs because we have an inflow and an outflow, meaning that we're depositing 27, 23 in the bank now, and the negative thousands mean that we're taking it out. So here, it's a little strange. You're putting money in and then you're taking it right back out again. But you would deposit 28, 59, 41, minus 1,000, minus 1,000, and then finally minus 1,000. And that's what these cash flows look like. All right. That's the difference between the two. Now, what about, I think we alluded to this yesterday, compounding frequency. Um, just like with annuities. Now, by the way, yes, annuities only take place once a year. The cash flows are annual, but there are other scenarios that you may run into where we have a similar situation where the cash flows are not every year, but they may be every month. Classic example of this is a car loan. When you take out a car loan, the bank makes sure that all the cash flows are the same. In other words, every monthly payment is exactly the same. So you can think of that as what you might call a monthly annuity, meaning that the cash flows are always a month apart, but they do take place every month. Therefore, it doesn't technically qualify as an annuity as far as English is concerned, but mathematically, we can use the same formulas with one adjustment in order to come up with either a present or a future value. Now, if you think about it, I mean, in practice, if you're going to have any kind of an annuity like this, it's typically monthly. Mortgage payments are the same. Every month is the same. Okay. Lease payments are typically the same every month. Rent is the same typically every month. So in other words, you see this in practice quite a bit. So what do we have to do to our formulas to adjust for the possibility that maybe the cash flows are taking place every month instead of every year? Well, what we have to do is take the cash flows, divide by M, and remember is the compounding frequency. And you notice it pops up quite a few places. So for the future value, this is what needs to be done to use it for annuities that take place more frequently than once a year. And again, we're assuming this is an ordinary annuity, which is what you'd expect with a car loan, for example. When you do get a car loan, even if there's a down payment, the first actual payment isn't due when you go to the dealer to pick up your car. Instead, it would typically be due a month later. Okay, so that would make it an ordinary annuity. The rent, on the other hand, is due at the beginning of the month that you're going to live in this apartment that you're living in. So in that case, you can think of your rent as an annuity due. And if it's an annuity due, notice the only difference here is that instead of multiplying by 1 plus R, like we did a little while ago, that has to be adjusted as well. So let me clean this up a little. Just so you can read it better. This is the formula for an ordinary annuity up here on the top. And if you notice here, instead of multiplying by 1 plus R, we multiply by 1 plus R over M. That multiplication also has to be consistent with the rest of it. Okay, so in our Excel examples, you notice how we multiply by 1 plus R because we're assuming annual payments. And by the way, with annual payments, M is equal to 1. So that is simply a special case of what you're seeing here. And then, of course, the present value would look like this. So again, all we've done is adjusted it by dividing out the cash flows and the interest rates by M and multiplying the time frame by M compared to what we did earlier. And now again, if you want to turn this into an annuity due, you're going to multiply by 1 plus R over M. Okay. That's how you would adjust for, let's say, monthly payments. And it will make a difference. Okay. It's important to keep track of how frequently these payments do take place. Now, by the way, if you want to later on, we'll see, you could take these formulas and rearrange them algebraically and figure out the size of the monthly payment that you would need, for example, to buy a $30,000 car, because then you would be solving for C. Okay, in other words, there's nothing to stop you from rearranging these algebraically to solve for the cash flow itself. All right, now here's a quick overview of where these formulas are coming from. And so let me just quickly go back and grab the PVA formula. This is now back to the assumption that these are ordinary annuities and annual cash flows. Okay, the traditional approach. So we're kind of wondering then, where did this come from? It's not obviously not self-explanatory. Where did we get this from? All right, well, first of all, when you calculate the present value of an annuity, what you're seeing here is what you're actually doing. You're actually calculating the present value of each individual cash flow all the way out to period end. And in fact, that's exactly what we did somewhere along the way. Oh, actually, no, I guess we only did that for future value, but still, that's what you're actually doing. So what you're going to do is replace 1 over 1 plus r with x. Okay, and again, this is just to make it easier to see what you're doing. And so that turns this expression into this. Okay, in other words, if you rewrote this as, it might be a little easier to see it. This becomes c times x, c times x squared, all the way to the end. Okay. Now with that being done, if you multiply both sides by x, of course, you're certainly allowed to do that. And here's the ingenious part. We're going to subtract one from the other. Okay, in other words, if I take this, in fact, here's what you're doing. Let's see it right here. The interesting part is that all the terms cancel out except for this one and this one. Uh-huh. So therefore, what you've got here, actually, I guess I kind of left out a step here. And then you divide out the 1 over x, so that brings us here. And then we factor out from the numerator cx. Okay. And again, why are we doing this? Just to make it easier to see what's happening. So actually, I'm going to copy this to the next slide so we can see it better. And remember, x is defined to be equal to 1 over 1 plus r. So therefore, we have now if I multiply through, you're going to get actually, I'm going to leave the c outside the parentheses just because the final result needs c on the outside anyway. So let's try this. Okay, that's good. So I multiplied the denominator. Actually, I multiplied 1 plus r by both terms in the denominator. In the numerator, I left it the way it was. And so you can see you've got in the denominator, you'll just end up with r. And that's actually the formula right there. Okay, let me go back and, oh, no, let me go grab it. Just so we can confirm it. Here we go. Yeah, I mean, up here we wrote is 1 plus r to the minus n. It's the same thing. Okay. So in other words, that's where it comes from. So the clever part was really right here. That's the trick. There's always a trick. Every proof has some little thing that if you didn't notice it, it's not going to work. Although I guess there's other ways we could do this, but you can see now why this formula works the way it does. Then if we do the future value, this is written in kind of an interesting way here because we know that there are n cash flows. The first one is being compounded n-1 periods. The second one n-2 all the way down to 0. In fact, that is exactly what we did here. Right. That's precisely what happened here. So same thing, x is no, oh no, sorry, this time x is 1 plus r. So once again, we use our clever strategy. Define FEA, x FEA, subtract. And you notice they'll all cancel out except these last two. And then we make the substitutions and we end up with our result. Okay, so that's all there was to it. And the great thing about this is it doesn't matter how many cash flows there are, 10, 20, 50, 100. It'll always be the same. All right, so now we're going to dive into a slightly different area here. Now, up to this point, we've been looking at the time value of money. It can be used to apply to really any securities in the marketplace, but it's particularly helpful in the area of bond pricing. Now, if you're not that familiar with bonds, it's understandable because all of the press is always, all the financial news you're hearing about, all the websites you look at, they're always talking about stocks. It's like they're obsessed with stocks. Bonds, by comparison, are considered, I guess, to be boring. In fact, there's a line about that in that movie, if you've ever seen it, The Big Short, which is about the financial crisis of 2007 through 8. And they start out by pointing out that, in the past, bonds were considered to be the dullest of all securities on Wall Street. Nobody wanted to work in bonds because they were so boring. But suddenly, all these different derivatives were invented that made bonds very exciting. In fact, the same derivatives that eventually caused the crisis. And because the basic structure is fine, very straightforward. But once you start turning it into a derivative security of some kind, then it becomes a very complicated product indeed. So a bond is basically a security that is issued by typically a corporation, but also governments. And all it means is that when you buy a bond, you're lending money to somebody. If I buy an Apple bond, I'm lending money to Apple. And in exchange for that, they give me interest payments for a fixed length of time, after which I get my money back. So a typical bond would look something like this. And, if we want, we could go look up the terms and conditions from some actual bonds. For example, suppose Apple issues a 30-year bond, which matures on, let's say, June 1, 54. Oh my God. The bond has a face value of $1,000. This is the amount that investors pay for in the bond when it is first issued. And this is the amount at which the bond will be redeemed on the maturity date, as it's called, of 6/1/54. Okay, now the interest payments are known as coupons. Okay, now in this case, let's just assume. Oh, and then the coupon rate is the percentage of the face value which is being paid to investors. For example, suppose the coupon rate of this Apple bond is 5%. This means that Apple will pay each year to the investors. $50 is known as a coupon. So in other words, you're paying $1,000 today, and then for the next 30 years, you get $50 in interest, which is known as a coupon. And in 30 years, you get your $1,000 back. So it's a loan. It's nothing but a loan, except that it is backed by the security, which you can sell to other investors if you need the money before the 30 years are up. If you lend money to somebody, you basically have to wait till they pay it back. But if you own a bond, well, you can collect the interest payments, but if you, let's say, decide to retire or something, you can sell the bond to somebody else and collect the money right up front. Now, by the way, in practice, though, it's a little bit messier than this. I'll mention this here, at least in the United States. Coupon payments are typically made on a semi-annual basis. In other words, half the annual payment or annual coupon is made every 6 months. So in other words, instead of getting $50 a year, you would get $25 every 6 months. So for this case, the investor would receive $25 every 6 months. I don't know how this happened. I mean, every country is different. Every country's bond markets are slightly different. The United States, this has been the way it's been for basically at least since the 20th century. Other countries, I believe Japan has annual coupon payments, but every country's bond markets are slightly different. So I guess, you know what, let me just try something here. I think I know where I can find some examples of Apple bonds. I find that this website is very poorly laid out. It's very difficult to find what you want. Wow. It used to be really easy. They've really, really made it even more clumsy over the years. Oh, I think we may have inadvertently found something. Oh, for God's sake. All right. I get it's really this is all stock data, by the way. I mean, it's really for the corporation, but I mean, this is company-wide data, but it really is meant for analyzing this company's stocks. I don't know why they had to make it so awkward. All right, well, this one we'll have to do. This bond was issued by Apple. See, now it's maturing in February 47. It doesn't tell us when it was issued, though. Oh, yes, it does. In 2017. So in other words, in February 9th. No, I'm going to remember this website. Investing. I don't think I'm going to bother with FINRA anymore. Investing.com. They actually gave me what I wanted. Um, so it was issued in February 2017. It was a 30-year bond at that time. It'll mature on February 9th, 2047. And the description tells me 4.25%, that's the coupon rate. So for $1,000 bond, the annual coupon would be $42.50. The semi-annual would, of course, be half of that, 21 and a quarter. And so you would be getting every 6 months this coupon payment. And if you still held the bond in February 2047, you get your $1,000 back. If you sell it before that, though, now here's the interesting part. The price, as we'll discuss in great detail, will be different typically than $1,000. It could go up, it could go down. The only times it's guaranteed to be $1,000 are on the issue date and on the maturity date. In between, the price of the bond depends on the level of interest rates in the economy. So that's where a lot of the risk is coming from. The fact that interest rates will affect the value of your bonds. And if you have to sell them when prices are dropping, you could end up suffering a loss. The other problem with bonds, at least corporate bonds, is that sometimes corporations go out of business. And if they do, the money you were promised is not going to come your way. It's just not going to happen. Okay. So that's called default risk or credit risk. So it doesn't happen extremely frequently. But like, for example, just yesterday, Red Lobster announced they're declaring bankruptcy. Now, they're declaring Chapter 11 bankruptcy, which means they plan on restructuring their debt so that they can continue in business. But the bondholders will probably not get the payments that they were promised. Okay, that's what bankruptcy means. Now, if they were planning on closing their doors forever, it would be a different kind of bankruptcy. And then they would just close the doors, and then a judge would dissolve the assets of the corporation and split up the value of the company among the bondholders. When that happens, it's unusual for anyone to get back more than 50-60% of what they paid for their bonds. Anyway, so what we're going to do here is try to understand how and why bond prices are different than the original face value once they've been issued. We're going to understand how bonds are priced in the market, and we're going to see that it's related directly to the time value of money. Okay. By the way, I want to show you the historical reason why these cash flows are called coupons. So let me go find if I can find a good example of this that will help you visualize why they're called coupons. Now, normally when you hear the word coupon, you're thinking in terms of going to the supermarket and saving $1 on paper towels, let's say. It's a little strip of paper which gives you $1 off. So what does this have to do with bonds? Now, sometimes it's easy to find examples of this. I don't know, it depends. All right, well, actually, we kind of got lucky here. Oh, this one looks good. All right. Now, I know it's hard to see it, but if you notice, it says the United States of America, 3% loan of 1898, $20. So in other words, in 1898, the US government issued this bond. And this 20 means that you're going to collect a $20 coupon payment every 6 months. And what's interesting is the bond certificate is up here on the top. This is what proves that you own this bond. It's an actual physical certificate. So this is 1898. There are no computers. But what's going on down here with these little strips on the bottom? Oh, I don't think. If I can magnify this a lot, you would see that, um, well, here's one over here on the left. This is a single coupon. Those little strips of paper are the coupons, which means that in order to cash in your $20 coupon, you had to actually take out a pair of scissors and cut the one with the correct date on it and take it to a bank, and they would give you your $20. In other words, you can see one right over here, a newer one. This one is based on a bond. Here we go. This is a bond. This is the date is June 15, 1969. This is a treasury bond that they issued in 1967. It was meant to be matured in 1972. It's a 5-year bond. The face value is $500 at that time. The coupon is 2.5%, which is $12.50. So every 6 months, you're entitled to a coupon of $6.25. But you must have this little coupon to collect your cash. So these are literally coupons. You cut them out, bring them to the bank, and they give you your money. And that's how it was done until computers came along. Huh. So, yeah, it's hard to find, these historical bond certificates as it is, much less with the coupons still on it. But sometimes you run across them. Like this one, somebody must have bought this and they never cashed in any of the coupons. So, but anyway, that's where the name comes from. Now, let's see. All right, so here we go. So here's the introduction. A bond is a debt instrument that offers investors a periodic stream of interest payments along with repayment of the borrowed principal on a specified maturity date. Interest payments are coupons. The principal is referred to as its face value, and the coupon rate is the ratio of the annual coupon to the face value. So, all right, so we now know what all these words mean. Sometimes you do see bonds that are issued without a coupon. Instead of paying interest to the investors, instead they're sold at a discount to the face value, and then you collect the full face value when they mature. So let's say you buy a bond for $900, and 10 years later, it's redeemed for $1,000. It means you made a $100 capital gain rather than coupon payments. Okay. So that you don't see as often, though. Most bonds in the marketplace do pay coupons. And by the way, I just want to mention here that most of the bonds that are issued in the marketplace either come from corporations or from the federal government. The federal government issues bonds to cover their deficits in the so-called treasury market. In fact, if you want to look at what they're offering, let's see. I think this is the right one. These are the bonds issued by the United States government. And what's unusual here is that you notice how there's all these different maturity dates. Unlike corporations, which tend to stick with 10, 20, or 30 years, the government, they're trying to borrow money because they need it in a hurry to pay their bills. And so what they do is they make all these different maturities available to investors. And really for the convenience of the investors, because they know there are people out there who want to invest for very short periods of time, all the way out to a full 30 years and everything in between. So they make these available to us because they need to borrow our money. Okay, they're in a kind of a bad spot. They have to cover their bills. So these numbers represent the coupon rates. Sorry, not the coupon rates. This is something a little different. I'll explain it to you when we get to that point. But in effect, this is more or less the rate of return you get from owning one of these bonds. And so these numbers are often referred to as the term structure of interest rates. And a graph of this is called the yield curve. So right now at this point in time, which is unusual, the short-term rates are actually a little bit higher than the long-term rates. Usually it's the other way around. But right now things are a little strange in the market. And we have a presidential election coming up. There's a lot of uncertainty. Most of the time, though, you'd expect to see the numbers going up. with the maturities. We'll explain that too when we go into that part of the chapter. Well, actually, the next chapter is where we discuss this. The next chapter is where we start to learn about interest rate risk. By the way, how do we know if a bond is safe? From credit risk, I mean. Well, treasuries are considered to be free of credit risk. The government is in a unique position. The government can raise taxes if they need to raise funds. They can sell assets. They have things they can do that a corporation can't do. So for all practical purposes, if the government offers you interest payments, you can be sure you'll get them. Corporations are different. Corporations can go out of business. So in order to make sure that you're not buying a very risky bond, there are two organizations that provide ratings to us. One of them is called Standard & Poor's, and they provide ratings for all these different bonds out there. And well, all right. I probably have it in the slides anyway, but the ratings range from AAA at the top, at the bottom, it's something like double D or D for the ones that are essentially bankrupt already. And the other one is Moody's. So if you're wondering, okay, so according to this, in August 20, this is the news we have right now. The most recent one I can find here is August 2022. S&P assigned AA plus, which is one level below the best. AAA is the best, AA plus is second best to Apple. Okay, so if you buy an Apple bond, chances of it going bankrupt, the company that is very, very remote. So you can be pretty confident that you're going to get the money that you were promised. Okay. So anyway, what you're seeing here should look familiar. You're seeing in this equation, the price of a bond is actually a present value. What is it the present value of? Well, these C's are now coupon payments, right? As we discussed, that's the annual or semi-annual interest rate. F is the face value, which you will receive in the final period of the bond's lifetime, which in this case is period N. So when you're calculating the price of a bond, you're calculating the present value of all the coupon payments you've been promised, plus the repayment of the bond's principal, which is known as its face value. Now the R here, that rate of interest there is determined by primarily the level of interest rates in the economy, the maturity of the bond, and most importantly, the credit risk of the corporation that issued it. Or in the case of the Treasury, it just is the lowest rate of interest you can earn in the economy for that maturity level. Okay, so now that's that R. By the way, in this particular case, this R has a very special name. When it refers specifically to a bond, this R is referred to as the bond's yield to maturity. It's the only market where we see this name, or sometimes it's just called the yield. That's the rate at which we discount or take the present value of the cash flows. And that's the number that reflects the risk of that corporation or the other issuer. But ultimately, you'll notice the bond's price is nothing but a present value. That's it, literally nothing but a present value. Now, luckily for us, bonds are easy to price because the cash flows are highly predictable. In fact, when you buy a bond, you're entering into a contract with the issuer called an indenture. And it spells out all the details. For example, the size of the coupon payments, the timing, any special features. If a corporation issues a bond and they do not live up to the terms of this indenture, then they can be declared bankrupt. Okay, so you have a very powerful incentive to make sure that they pay you when they're supposed to. And so, and they will, as long as they have the money. But if you're talking about Red Lobster, well, that's a different matter altogether. Now you can write this a little more simply. You notice what's happened here is we simply have a sum of all the cash flows. And the subscript here is T. T means the time at which the cash flows are received. This is a fixed constant. Okay, so in other words, if you want to calculate the present value more quickly, you'll notice this is nothing but an annuity of coupons. It may be a semi-annual annuity, but it's still an annuity because every coupon is the same. So calculating the present value comes down to computing the present value of an annuity plus present value of a sum. And there's your bond price. Oh my God, is it really that straightforward? Yes, it is. And by the way, I just want to point out too, you may have heard this phrase before, because these cash flows are so predictable, thanks to the fact that they're legally required, bonds are often referred to as fixed income instruments. Or fixed income securities. Compared with stocks, for example, where the cash flows are very unpredictable. So that makes things a lot simpler for calculating bond prices than stock prices. Okay, stock prices require a lot of other considerations, but here it's really just a straightforward matter of determining the present value of these cash flows. Interesting. So just as a quick example, suppose that a bond is issued by the U.S. Treasury, 4 years remaining to maturity. At that time, when it matures, the owner will be repaid the full face value of $1,000. The coupon is $70 a year. The 4-year interest rate or yield in this case is 5%. What is the market price of this bond? Okay, well, if you just did it directly like this, you can see, we could plug this into Excel, and you would see that the price is $1,070.92. Now, here's an interesting question. If the yield went up, well, algebraically, you can see that you're increasing all the denominators. The price has to fall. If the yield falls, of course, obviously the bond price rises. In other words, there's an inverse relationship between interest rates and bond prices. Interest rates go up, bond prices go down, and vice versa. So in an environment where rates are heading up, bond prices are going to lose money. In an environment where rates are dropping, the opposite will happen. This is why everyone pays so close attention to what the Fed says when they decide to announce, in the future we may raise rates, we may lower rates, because that has a major impact on the price of every bond in the marketplace. Now, anyway, so this is a very complex discussion here that we will get back to next time. But let's just cut it off here. I think we discussed a lot of important ideas here, but I want to make sure that we don't rush through this. I'd like to especially go through some examples in Excel. And anyway, so I guess we'll stop right here. And then next time we'll pick it up with some bond pricing examples, and we'll try to show the relationship between pricing and interest rates. And that will lead us to a discussion in the next chapter about interest rate risk. But we're also going to introduce some more complex ideas And then pretty soon, I think we're gonna have to start reviewing VBA so that we can start writing some basic code, because we're reaching that point very quickly where we may want to do some actual programming. And basically what you're doing is the same thing you're seeing here, except that you can automate it, or you can do more, get more results very quickly. So anyway, I think we'll stop right here. And then next time I see you, we will dive more deeply into bond pricing. We'll do some more examples in Excel, and then we'll see what happens. But what we're leading up to is a discussion about interest rate risk in the bond markets. Okay. So, all right. So hope you find this interesting. It's certainly useful. I mean, you may actually own bonds and you may not even realize it in your own retirement accounts. So anyway, I'll see you all next time.